Um, and last but not least, in this first session, I will turn it over to Kurt Terrani from Oak Ridge National Lab.
Okay, I need to unmute myself. I believe I did. I'm going to go to full screen, so hopefully you can see my screen. Give me a thumbs up, Lauren, if you can. You do. Okay, very good. Lauren, thanks a lot for moderating this session. And again, thanks to Lou and crew here organizing the workshop. I usually participate on the sidelines. Usually there's good coffee and food, but this time we get to do it on our own. So maybe, as Everett said, we'll do it again next year. Appreciate the opportunity to talk to you today. I've been set up really well by the prior speakers, and I'm going to go into a little bit more in the weeds, in the technical areas, and really what I want to touch is opportunities to bring in advanced technologies that are available to us today to do advanced reactors, deploy them in a better way, cheaper way, faster way. Okay, I'm going to just kind of touch a little bit on since I have the podium, talk a little bit about additive manufacturing. It's not one way of doing things. There's a myriad way of doing things. So I'll touch a little bit on that. And then obviously I'm the director of the Transformational Challenge Reactor program here, and talk about how in TCR, the 4 areas where we're tapping into additive manufacturing, often in combination with artificial intelligence techniques, to try to elevate technology in 4 distinct areas. And I'll give you examples of that. And the purpose of this is at the end of the day, you need to see these as tools in your toolbox when you go ahead and deploy these advanced reactors. And you'll see there's some very exciting technologies. And the premise of this is that, you know, if we were going to build advanced reactors the same way we did in the 50s and 60s, there's something wrong. There's new technology available. We need to capitalize on that. And I'll talk about some cool opportunities that are ongoing and are available to us. Okay. Additive manufacturing, we're building components small volume by small volume. Generally, there are 2 different categories. On the right, you see a direct deposition technique. Something comes in and deposits material. It can be, you know, it's not just plastic. It can be metal. It can be ceramic. It could be concrete. They make big, you know, they deposit big chunks of concrete with this. The benefit of this is that you can make really large structures, very, very large volume. You can see they can make the steel structures up to 7 meter cube. You have some surface roughness complexity and a complex toolpath design with these direct deposition techniques. The other way of doing things, you see it on the left, is powder bed techniques, where you have a bed of powder. It could be a bed of slurry. Again, it can be plastic, metal, ceramic, you name it, and you come in and you fuse them in 2-dimensional layers together. When you go ahead and do things this way, you can have really, really ample geometric complexity. You have very, very, very good surface finishes. However, your build volumes are smaller, and you're limited to single materials. Okay, but just remember that there's 50 techniques on the left, and there's 50 techniques on the right. So really, the world is your oyster on how you can do things. To give you an example of the stuff on the left, the powder bed techniques, you see these are some of the experimental conceptual components that we're making here for TCR, and you basically see a stainless steel part being manufactured. Look on the left, you see this, there's a video of part, we're monitoring the part as it's being built, so we're getting a lot of information for every small volume of the part as it's being built, and I'll talk a lot about that in a few slides about why is this information important. To give you an example of the direct deposition techniques, I've shown a slide here. This is a very large system called Medusa here at Oak Ridge, and it's got 3 robotic arms, and you can deposit 2-meter diameter, 2-meter tall steel structures, right? So additive manufacturing is not something where you make a paperweight for your desk. You can make large structures, and you know there's opportunities there. So the question is, how do we use these technologies to do something we couldn't do before? All right. So I talked about in TCR, this is exactly what we're trying to tackle, is figure out how do we use specifically additive manufacturing as the core motif here, and also combine it with other advances in computational sciences, specifically artificial intelligence and material sciences, to deliver new technologies that were not available before, and use these technologies towards the deployment of better, faster, cheaper advanced reactors. Okay, There's four specific areas, and you get to read a lot more about that on our website, tcr.ornl.gov. But really, the four areas we're targeting. The first one, all the way to the left, is when I'm using additive manufacturing, I'm no longer stuck to a simple shape of a rod or a sphere or a plate. Now I can have all kinds of complex geometry. Okay, there's a reason your body is not a 90-degree flange and straight pipes. It's got all this complexity in it because it's enjoyed billions of years of evolution, and it's a high-performance complex machine. And so this opens the door for us. Now, navigating this complex design space, when you have this many degrees of freedom, is complicated. And this opportunity that's given to us by additive manufacturing, how to navigate that space, it's an interesting computational problem, and artificial intelligence tools can really help there. So I'll talk a little bit about that. The second area is leveraging additive manufacturing to make something we couldn't make before. So I'll show you examples. These are some of the conceptual blocks for as TCR fuel elements, and they're 3D printed silicon carbide. So silicon carbide is a dream material in salt systems. We know it's got incredibly good environmental stability. It's got very, very good irradiation stability. There's data out of HIFER up to 100, 120 displacements per atom. In a temperature regimes that most advanced reactors are interested in, you're cruising, right? You're getting irradiation, induced irradiation resistance, which is fantastic, right? So how do we exploit AM to make this high performance material when we couldn't make it before? The third area is also really important, is integrating sensing into these critical structures, right? So we run plants. Everett mentioned. I mean, it's remarkable how the nuclear community runs plants. The highest capacity factors for decades, better than any other energy source. Amazing operational excellence, and they're doing that with sensors not really in the core and integrated into structures around the plant. Imagine you have a lot more data coming from your system. Imagine you have integrated sensing into your critical structures. You're not just doing health monitoring, but you're also getting a lot more stream of data, and that's key if you're serious about autonomous or semi-autonomous operation. Why do you want semi-autonomous or autonomous operation? Because it's expensive. Because running a plant with 400 people is a lot more expensive than competing with a combined gas cycle plant when there's 7 people doing it. So again, these are critical enabling technologies. The last one, very, very important one we're very passionate about here at TCR is, again, exploiting the inherent nature of additive manufacturing, where I'm making a material small volume by small volume, continuously monitoring our process, extracting large data sets from our manufacturing process, and using that data set to ascertain the quality of my component. We spend a lot of money after we make something, putting that end stamp on it. It's expensive, it's time consuming, and it adds to the nuclear cost. And how do we use automated techniques to remove human beings and reduce time and cost of making critical nuclear components? Okay, so let me dive deeper into each one of these areas. The first one we talked about was complex design. Think about it, I showed you these cog-shaped elements. All I'm showing you on the right is these elements. These are fuel elements. They're generating heat. And then you can see the blue is where kind of cooling channels are, right? So this element's being cooled. Now, no longer, when I went to school, they said, hey, make sure somebody can machine it, make sure somebody can manufacture it. I get to throw that law out the door. Now I can have any geometry that I want. So instead of a perfectly round circular cooling channel, I can have this kind of snake tongue cooling channel, or I can have this wishbone cooling channel. Okay, when I do that, you see my temperature drop in my fuel element comes down, my stress comes down. So I can really change things with complete freedom to achieve performance parameters. What's the benefit of this? I have a safer system. I have a higher performance system. I can extract more power from my system with safe conditions. Now, changing this arbitrary geometry is complicated. You see on the left, they parameterize this complex geometry, and they're trying to figure out which one is most optimal. And so doing that is the most efficient way of doing that is actually using AI techniques to explore this optimization paradigm. And this is one of the areas we're working on. Again, the goal here is to show the art of the possible. I'm not asking you to come use this fuel element. I've decided for everybody. I'm trying to establish the framework for you to solve a complex multi-physics problem using an AI optimization scheme. So that's one of the areas that we're trying to we're trying to kind of introduce these thoughts to the community and have the community benefit from these possibilities. What's this, the second area? We talked about it. Again, I'm going to go back to the silicon carbide example, even though we're advanced manufacturing a lot of different materials here too. We get to 3D print silicon carbide. Oh my God. You know, it used to be you have to get a large piece of silicon carbide, you have to machine it, or you had to use other techniques that didn't really give you the nuclear grade silicon carbide. Now we get to 3D print silicon carbide in these very, very complex geometries. You see in the middle, there's an X-ray tomography of one of our conceptual fuel elements. All those white dots are trace of fuel particles embedded in this 3D printed silicon carbide. So again, look at the possibilities that are available, whether it's for a salt reactor or other reactor. And again, you're not stuck with this system. You can have other material systems that you can explore. Now, we are obviously, we are developing advanced manufacturing techniques for these high performance nuclear materials. However, it's very important, you got to bring data. This is, you know, interacting with NRC is very easy if you have data. Bring data, talk to them. They're very, very reasonable people, but you got to show the data. And so what we do, we immediately go ahead and do irradiation testing on these materials. So at the bottom right, you see some of the capsules that were irradiated in our reactor in our backyard, high flux isotope reactor last summer. So we irradiated about 25 capsules last summer. And that figure on the top right, just all it's saying, it's a confusing figure, but all it's saying is that it's showing that the strength of this 3D printed silicon carbide is not changing before and after irradiation. And basically, this is what we mean by irradiation resistant material. So it's been irradiated from 400C to about 800C, and there's no change in its strength from before irradiation to after irradiation, okay? So again, now this is an example of using additive manufacturing to make an advanced material that's a very high performance nuclear material and supplying the data for it and being able to actually use it to make advanced reactors. Okay, the third area, we talked about it quickly, is integrating sensors. To the left, you know, you usually have your temperature sensor, your neutron flux sensors somewhere away. You're getting information. You have to kind of extrapolate what does this information really mean in locations that you care about? And they're sparse. You're getting point information, right? So now with integrating sensing, and you don't have to 3D print the sensor. We're not focusing on that. There are other folks that are working on that. But even existing sensors, there's optical fibers, there's ultrasonic sensors, where you get to get distributed information. So you have one line running, you're getting information along the length of this sensor, integrated into structures that you care about, your fuel structure, your structural components, where you're curious if there's a crack growing, you're curious about, is this thing creeping? So now you can do incredible health monitoring. You get a lot more information from your system. And again, these are key enablers of having a reliable and safe system and having a system that can have autonomous or semi-autonomous operation. So again, we're exploiting additive to really target this area as well. And the last area is what we call our digital platform. So there's this incredibly busy slide here, but bear with me. The way we do things, I'm talking about existing materials that you're building and putting into your reactors. We have a line that's nuclear quality line. We have procedures. We have quality assurance people. They inspect at every step. We write these procedures. Somebody comes and reads. And then we do them in kind of discrete steps with information. There's a run sheet. We write all the stuff down. And then we promise ourselves that we're going to follow this information. And then we hope for the best. We put them in these reactors and we hope they don't fail. And that's kind of how we do quality control. So this is what we're trying to do this very, very differently. Start with me at the top left. We have a design, right? We go in at the bottom left. We start an additive manufacturing operation. As I showed you in that slide earlier, we're monitoring our build process. So we have digital data coming in for every small volume of the part as we're manufacturing it. We have automated data coming in from our feedstock. We register all this data into a database. When we make a part that's about the size of this coffee mug, we have about 100 to 200 gigabytes of compressed data associated with this for every about 50 micrometer voxel of this part. We track the part, okay? It's all done in a database, in one coherent continuous database through these different operations, heat treatment, metrology, subtractive operations, sectioning. All of this information, all the information from the machine, all the information about the part gets registered into this database. Then we do campaigns of testing on select samples to the right. These are location-specific testing. So no longer we cut a batch from the end, and then we hope that it's representative of the part. When we do testing here in this location, we go and look at the data we collected during manufacturing from that location, and we try to correlate what we see for a specific sample from a specific location to what we saw during manufacturing. And this is the holy grail of it, is correlating what we see during manufacturing, whatever we can see, to properties that we care about, right? And this is where, again, AI comes in, machine learning, being able to train a machine learning algorithm to have strong correlations between what we saw during manufacturing and what we care about as a properties of the part. And once you establish this correlation, you have an automated system that the moment you're done making the part, it can tell you whether the part meets the quality rigor or it doesn't meet the quality rigor. And that's a really big thing. First of all, it's a far more data-rich approach than what we're doing today. And imagine how fast it is, how fast it's automated, it's fast, and it's going to be significantly cheaper. Where again, this is, we're fortunate to have participants from NRC that are actually embedded in our team with us here. And we're trying to showcase this framework. This obviously, again, a framework that's not specific to a reactor or material. It's very broad, and it's actually beyond nuclear. It applies itself to any critical application. Okay, so we talked about the four areas: advanced designs, materials, integrated sensing, and on-the-fly qualification, all enabled by exploiting additive manufacturing techniques, artificial intelligence techniques. Okay, so these are four technology areas. We're trying to elevate their technology readiness level, showcase that these are mature technologies, hopefully through a demonstration. And then at that point, they're going to be ripe for industrial adoption. This is key. Everett mentioned accident tolerant fuel, and it was the same thing. I think it's unreasonable to expect industry to come and adopt technology at TRL 2 or 3. We really need to get it to 5 or 6 and 7 in the national lab system using DOE support, and then codify it, proceduralize it, and then have folks adopt it. So let me give you examples of cases where we're already doing a transfer of some of this knowledge and capabilities. This was a very fun project with Kairos Power. This is their pump impeller for molten salt. They had a design. It's an awesome high performance design. They understand the design, they understand analysis, but it's a difficult part to make, right? Look at the complexity of the part. And so what were they going to do? They had to go ahead and cast that. There's timelines. These are not, you're not making 10,000 parts. So this is where additive shines. And so they came here. We got to work with them. We get to understand their design, and we basically manufactured this pump impeller for them that they're testing. And so they're testing. They're telling us how it's performing. And you see, it's a physical impeller that was manufactured. They're testing it, but we also have on the right, you see all the digital data that we got during manufacturing. So if during testing they come in and say, hey, this one blade had an issue, we get to go back and take a look at our in-situ manufacturing data, if there's a correlation between what we saw during manufacturing and that absence of performance in that specific location, right? Now, as Everett mentioned, we want to get to advanced reactors, but boy, the current fleet are also very important. We can't lose sight of that. So again, in recognizing that truth, we work with our good friends in Tennessee Valley Authority and Framatome. And so we 3D printed fuel assembly brackets that are going into TVA's Browns Ferry very soon. They've already been assembled into fuel assemblies. What's special about these? These are the first safety-related 3D printed parts that are going into a nuclear power plant ever, okay? So now we see, okay, all right, additive manufacturing looks cute on my desk. Additive manufacturing, we're making some components. Additive manufacturing, safety-related part going into a commercial power plant. So it's, this is our goal, to elevate the TRL, technology readiness level, for these systems. And again, they're also the first components 3D printed that are going into a plant that have this in-situ manufacturing data behind them, okay? And this is key. Again, this is key when you talk to a regulator. You gotta back up your claims with data. And so this is a very fantastic test case for us to be able to say, hey, we tested this material and we have this in-situ data, and we're gonna correlate the performance of these safety-related parts to the data we collected during manufacturing. So with that said, I want to wrap up. I think we'll leave a few minutes for discussion, and hope that I inspired you to think about how you can take advantage of some of these advanced technologies to realize advanced high-performance systems.
Thanks so much for that presentation, Kurt. That's really exciting stuff. We have gotten a few questions, and so we'll hit at least one of them here. And the first one that came in was, have you found that additive manufacturing materials tend to be more radiation resistant than traditionally cast materials due to the differing grain structure?
So that's an excellent question. Usually in metal systems, because of the very rapid cooling rates that you get in the material, you get a very fine grain structure full of dislocation networks. Like we see this very often, like in stainless steels or even ferritic steels. And those dislocation sinks, they tend to act as sinks for radiation defects. So again, a lot of the material that was irradiated in HIFER was also metallic materials. We have a publication. We have actually a special issue of Journal of Nuclear Materials that we organized around additive manufacturing for nuclear energy. It's forthcoming. I'm the guest editor of that journal. And the long answer to your question, yes, because of these defects that are introduced during manufacturing, but it depends on how you manage the material after additive manufacturing. And it really depends on that. So there's a lot of good detail available in that journal. I encourage you to go over there. Lauren, is it okay if I just read through the Q&A and answer them?
Yeah, maybe we take like one more question here if there's a good one, and we can follow up on the other questions in the Q&A box.
So one of the questions, Bell is asking, would the current neutron detectors withstand high temperatures when embedded in the fuel? So Bell, again, it depends on where you embed it. Do you embed it in the high temperature region of the fuel or in regions that can withstand the temperatures? And then during additive manufacturing, that's a very kind of a harsh process itself. And the trick is to embed sheath that then you insert the sensors into. So again, it really depends on the details. So how about that? I'll try to answer these questions on the chat and maybe open it for the whole panel to have some more discussions.
That's perfect. Thank you so much, Kurt. And yeah, thank you again to the other speakers as well. So thanks to Christian, Wendy, and Everett. Thanks for having us. David or Lou, I'll turn it back over to you guys to tell us what's next.
All right, thank you, Lauren. Thank you once again to the panelists for providing the conversation. We're very interested in what's going on in all these areas. Our next session is going to be the international session. We actually have a few more minutes to answer questions on here because we're going to do what we have been doing, which is our AV check between 10:30 and 10:40, and then we'll get started on time at 10:40 with the international session. On there. So if Kurt, if you'd like to answer a couple more of the questions, we've got about 5 more minutes in this session.
Sure. Yeah, I'd love to. Jose mentioned, what is the limit of metal selection for direct deposition techniques? Again, it depends on the technique, whether it's a wire deposition or powder deposition. The powder deposition methods are very versatile. In fact, you can grade, you can start with like a nickel-based alloy and transition to iron-based alloy or anything else. So as long as you can melt it, you're a go. With the wire deposition methods, you need to get the wire, and sometimes it's difficult to get the wire. There are tricks where you get a wire tube and fill it with powder, and then you print that, but I mean, are you really getting the right material? So that feedstock production on the wire techniques is a bit of a challenge. I hope I answered that. Jakob was asking, how does additive manufacturing handle the challenge of large scale production? This is, that's an area that's being considered in nuclear and beyond nuclear. Big area additive manufacturing is a very thriving area. They are printing large concrete structures. They're printing large metal structures. So I think the sky is the limit. If the right problem comes in, there's a lot of potential solutions there. Microreactors and SMRs are really ripe for what's available today. So I think if you want to make a vessel, like a boiling water reactor vessel, 4-meter diameter, 8 meters tall, I don't think that the industry is able to respond right away. But in a lot of these microreactor systems, the technologies are very ripe. Is this good, or should I answer?
Want to do one more? I think Raluca's got an interesting one about grading functional grading of material.
Yeah, that's so. Raluca's again asking a very good question. There is a lot of opportunity. You remember I showed these slides. I said on the left is powder bed techniques, on the right is direct deposition. You really do functional grading in the direct deposition, where you can change. You can change the composition of your material. Now, grading can also be changing the microstructure along the way. And so it's additive is actually really made for that. It's really the way I'm using it today at these early stages is very boring. We're making single materials. We're trying to just supply the base here, but I think there's a lot of opportunity there. There's a very, I encourage you guys to go look this up. There's a very nice piece of material where it's a nickel-based alloy, and if you polish it, you see a picture of Mona Lisa, and it's literally all the difference is that the way they melted the material and they gave it a different grain structure. So you can tune grain structure, you can tune grain size, you can tune elongation, you can tune composition. The sky's the limit, and thinking about how you exploit these opportunities is really, I think, the next big thing.
Okay, with that, I think we're getting into our, we're planning on the, thank you again, Kurt.